Hello everyone, welcome to GATE Pass. In this video we are going to take two remaining problems which appeared in 2019 GATE and that were related to thermodynamics. So this was question number 39 which appeared for 2 marks. Let's briefly first see what the problem statement is. So you have a mixture of steam plus water in a vessel, okay, and this is a variable volume vessel. The initial temperature and pressure are given as 180 degree and the pressure is constant. So essentially they have told you that the temperature and pressure, they remain constant throughout the process, okay, but the initial volume is 1 meter cube and this volume is allowed to change, okay. So now there is a wet steam inside this vessel and over a period of time it loses heat and the quality of steam decreases, okay. So initial conditions have been given as the quality of steam is 0.5 initially when the volume was 1 meter cube and final quality of steam was 0.1. Now they have told you that this system, it loses heat at a constant rate over a period of 10 hours, okay. So this was the condition of the steam after 10 hours. So you have to calculate what is the rate at which the heat is lost. So that was the question. Further they have given you the data. At 180 degree centigrade, mind it, temperature and pressure are held constant and only volume is changing, okay. So data like this specific volume, specific internal energy and specific enthalpy of both the vapor and the liquid phase, it has been given, okay. You can see that they have been taken from the steam table. Fine. So let's first understand what is happening. In this case, I am going to explain the process on the PV diagram. So you all know that under this bell-shaped curve you have your two-phase region where your vapor and liquid, they are in equilibrium with each other. To start with, they have given you that there is a quality of steam, that means 0.5. So that means a fraction of your water is in the vapor state and the remaining is in the liquid state. So you are basically in this region, which is a two-phase region where the liquid and vapor are coexisting, okay. At any point on this, so let's say that this is my isotherm which I have drawn at 180 degrees centigrade. So let's say that initial volume is V1. I am starting from this point, okay. And when it loses heat at constant temperature, so I am moving on the isotherm and the pressure is also constant, okay. So at constant temperature and pressure, when the system is losing heat, so the process is in this direction and it reaches certain volume V2 at which you have now your final quality of steam as 0.1. Now you have to calculate how much is the heat lost, okay. So this is your process basically on the PV diagram. Let's quickly see what is quality of steam. It has been defined as the mass of the vapor divided by the mass of vapor plus liquid, okay. So it is essentially a mass fraction. So any other specific quantity which you want to calculate, you can just do this simple mathematics and you can calculate it. So I have given you the formulas. So let's now tackle the problem. So what you have to do is, first of all, let's see what equation you have to use. So this is a closed system. For a closed system, you can write that your change in internal energy, that is equal to Q plus W, okay. Now where my sign convention is that the heat supplied to the system, which goes into the system, that is positive and work done on the system is positive, okay. So that's what is the sign convention I am using. This is the constant pressure process and we have seen in one of the previous videos that for a constant pressure closed system, you can write that your Q, that is equal to your change in enthalpy, and since over here it has been given that this is specific enthalpy, so I have to multiply it with the mass, okay. Now, so the first step will be to calculate your mass and then your change in enthalpy. Now, how am I going to calculate my mass? So that I will calculate from my specific volume, okay. So initially your quality of steam is 0.5. So what will be the V, that is equal to X times Vg plus 1 minus X times Vf, okay. Now X initially is 0.5, so it is 0.5 times your 0.19405 plus 0.5, that is 1 minus X times 0.001127, okay. So now your specific volume for the initially for this system is then if you calculate it, it is 0.0975 and the units are meter cube per kg. But to start with, what do you have? Your total volume is 1 meter cube. Total volume is 1 meter cube. Okay. So then from that, because this is your total volume, so that means it is equal to what I do is that in order to calculate the mass, I have to divide my total volume by this specific volume. That will give me my mass. Okay, so I am going to do that, 0.0975. So that comes out to be the value as 10.247 kg. Okay. Now this is the closed system, mass is not leaving, so this mass is going to remain constant. So that's what I am going to write over here before erasing it from the board. So it is, total mass is your 10.247 kg. You have calculated it from the initial volume, okay, and by calculating this specific volume which was present, okay. So mass I have calculated. Now the problem is very easy. You have to calculate your delta H, and your delta H is nothing but final. If I say HF, it will create confusion. So I will say H2 minus H1. Okay. Now let's calculate what is your H2. That is your final enthalpy of the system. Okay. When your quality of steam is 0.1, so what I am going to do is, okay, so it will be 0.1 times Hg, so 2778.2 plus what is 1 minus x now? In the final stage it is 1 minus 0.1, so 0.9. That will be the mass fraction of the liquid multiplied with the specific enthalpy of the liquid, which is 763.21. Okay. And your H1 will be initial enthalpy, specific enthalpy, okay, that you are going to calculate, because at that time your quality of steam is 0.5, so 0.5 into 2778.2 plus 0.5 into 763.2. Okay, so this gives you your initial and final enthalpies. Now what will be the difference? Calculated H2 minus H1, that will be equal to your minus 805.996 kilojoules per kg. Okay, now everything is now simple. So you can calculate your Q, that is the total amount of heat which is lost in 10 hours. That I will do by multiplying M with this H2 minus H1. Okay, M is 10.247. Multiply it with 805.996. There is a minus sign over here. And what you get is that Q is equal to, if you do this calculation, okay, so the final value is minus 8259 kilojoules. Okay, so this is your total amount of heat which is lost in 10 hours. Okay, so but you have been asked to find out the rate at which heat is lost, so you have to divide it by 10. Okay, so in order to calculate your Q dot, I do not have space, I will erase something. So over here Q comes out to be minus, that means heat is lost by the system. Okay, so you have been asked to calculate Q dot, which will be nothing but 8259 divided by 10, that is 825.9 kilojoules per hour. So the heat is lost, the heat is being lost at the rate of 825.9 kilojoules per hour. Okay, so this is the answer which is given in the key. Okay, so the second question is question number 40. It came for 2 marks. In this case, they have given you that an equimolar mixture of N-propane and N-butane is being fed to a distillation column. Okay, and the condensate which you get, it is rich in propane. So there is 95% of propane and 5% of normal butane. Okay, now this condensate which you are obtaining is a saturated liquid at 55 degrees centigrade, and they have asked you to calculate the condenser pressure. Okay, they have asked you to use Raoults law in order to solve this problem, and when you use Raoults law, we have seen in the last video, you need the values of saturation pressure. So to estimate saturation pressure, they have given you Antoine's equation. The coefficients A, B and C which have to be used for N-propane and N-butane, they are also given. So it's a very straightforward problem because you have to calculate just the bubble point pressure, and you all know how do we calculate it. Let's write first the Raoults law for both the components. Let's say if my partial pressure for component A, that is equal to mole fraction XA, then I have to multiply it with PA saturation. Okay, similarly I can write my Raoults law for component B, XB, PB saturation. Okay, now from Dalton's law, you know that your total pressure, that is equal to the sum of partial pressures. So for what you have to do is first calculate your partial pressures of N-propane and N-butane, and then you have to just add them. If I add them, then this is equal to XA PA saturation plus XB PB saturation. Okay, now you can quickly evaluate what is your PA saturation. Mind it, don't forget to convert your temperature because it is given in Celsius, and here they have given you the formula where you have to put your temperature in Kelvin. So 55 degrees centigrade, that will be equal to 328 Kelvin. So it will be 328 plus C. Okay, if I plug in the values of A, B and C over here for your N-propane and then do the calculation, I'm going to directly write the values of the saturation pressures which I get, so that when you are doing calculation you can check whether you get the same values. So it is 18.59 bar for propane and you have 5.57 bar for N-butane. Okay, now simply plug these values in this equation with the values of XA as 0.95 and XB as 0.05, and you get your total pressure, which is equal to 17.939 bars. Okay, so this is a very simple problem. The only catch over here is that if you forget to convert your temperature from Celsius to Kelvin, then it might create, it might give you a wrong answer. That is the only catch. Otherwise, your bubble point pressure calculation, it is very simple. Okay, so I hope you understood the way I teach, and if you like this video, please don't forget to comment and also like my video and subscribe to my channel, and thanks for watching.